Caleffi, and happy Thursday to you as well. Today we are doing an awesome Coffee with Caleffi webinar. We're going to be talking about the water demand calculator, and maybe you tuned in for one of the previous Coffee with Caleffis where we did also talk about the water demand calculator. We're bringing back our same awesome guest speakers from IAPMO, and I'll introduce them here in a little bit. But first, before we get into that webinar on how to use that water demand calculator, the benefits you can see, we're going to talk about just some of the quick questions that we get pretty regularly that have to do with the GoToWebinar software. So if you are having any troubles with audio, you're seeing my lips move but nothing's coming out kind of thing, definitely go ahead and restart, back yourself out and join back in again, and we can make sure to get you taken care of there. If you're looking for a copy of the presentation, at the end of the webinar, we will have a survey. You can click yes, I want a copy of the presentation. Otherwise, we actually have it in the materials section of GoToWebinar. If you click on the icon for materials, it might be labeled as handouts. You can download it there as well as a PDF. So from there, if you are possibly having to leave us early today, maybe you got an appointment or whatever, you want to watch the rest of it, we actually record all these webinars. We put them up on YouTube. Usually they're up by early next week, and you can watch it there and pause it as needed and catch up with whatever you might have missed. So moving on to the next slide there. If you are attending with us live today, you can actually get a certificate of attendance, or you will be getting a certificate of attendance. So if you can use that for your professional development hours, definitely go for it. It varies state by state and jurisdictions and everything else, but definitely look for that in your email inbox. And then next slide. Alrighty, and like always, we are always going to be pushing our hydronics journals, right? So these are a great resource. And the next one that is coming out is going to be talking about zoning and hydronic systems. I believe this is one's pretty close to being hot off the presses here. So definitely, if you're getting these in the mail, check for it in your mailbox, and you'll see it on our website, hydronics.caleffi.com, where you can download it there as a PDF. And then next month, we've got Max Rohr coming back with us to talk about pressure reducing valves and plumbing applications and understanding some of the weird little projects that you might run into and giving you some potential problems and solutions to go along with it, right? So definitely be around for that and check out that one with Max next month. And with that, we are going to welcome our guest speakers from IAPMO. We are so happy to have them back again. We got Mr. Christoph Lohr, and from IAPMO, he's going to be the Vice President of Technical Services and Research. We got Toju Omaghomi, who is going to be the Industry Research Manager for IAPMO. And again, thank you guys so much for your time today, and I'll leave it with you. And if anybody does have any questions, definitely make sure to put it in the questions pane. We'll try to get to them as quickly as we can, and enjoy the show.
Excellent. Thank you, Cody. Thank you for that warm welcome, and it's really good to be here with Toju. We were hoping to have Randy and Dan with us. Unfortunately, they got pulled away last minute on a couple other things, but the presentation is one that actually Randy and Dan and everyone has had input on. So you're still getting the best of the best in terms of the information that's going to be available today. Just worth mentioning here, one of the things that we were excited about, there was some collaboration between Caleffi and our our International Water Sanitation and Hygiene Foundation, IWISH. And if you're interested in any kind of that philanthropic work, there's a website with a QR code there. We mentioned it on the last one. Wanted to mention it out again today. Just a big shout out to that part of IAPMO and that arm of ours that does a lot of really good work across the world, really. And then in addition to that, we have our new Innovation and Research Fund. This is one of the engines that's really supporting a lot of the research we're doing, including around the water demand calculator and looking at commercial buildings. So if you want to learn more, check out that website. The QR code there will take you to the Support Innovation website, and you can learn more about some of the work that we're doing. And just as a reminder, last time, back in June, myself and Toju, along with Dan, we gave a presentation on specifically the impacts that the water demand calculator would have on hot water systems. We had a really great turnout. Hopefully a lot of folks of you that are here today came back for this one. That one kind of talked more about the benefits and some of the math behind the water demand calculator. That QR code there will take you to the Coffee with Caleffi website, where you can YouTube website where you can watch that if you want to get a refresher on that. But it was a really great session, had a lot of great questions, and that's where this presentation that I'm presenting today was born out of. We had a lot of feedback on 3 specific items. So the title for today, the Water Demand Calculator in Practice, with a focus on designing hot water supply systems. We're going to cover a little bit of the cold water and hot water side, but really the emphasis is going to be how it impacts hot water today. Fortunately, the cold water and hot water methodologies are basically the same, but we'll touch on some of the nuances as we go through. So there were three objectives that we kind of came from what people were wanting from the last go around. One was project profiles and success stories using the water demand calculator. Also looking at working with the calculator and running the numbers. So that's what the bulk of the presentation will be today, and including we're going to showcase the WDC Pro if you're interested especially for the multifamily. It's a great tool. And then at the end, putting it all together, evaluating the water and energy efficiency potential. We got a couple of slides there that kind of will address that. But again, the bulk of the work is going to be on that working the calculator today. So first off, wanted to start off with some project profile and success stories. It's tough to know everywhere where the water demand calculator is used, but we have a number of them that are out there that are pretty high profile that people got really excited for, and really a lot of the success comes from looking at some of the numbers from different areas, and really the first one is the Nueva Esperanza project in Hillsboro, Oregon, which I believe is a suburb of Portland, where they saw reduced system development charges by almost $400,000, cost savings of $2,650 per unit, and downsizing the water meter and water mains from a 4-inch down to a 2-inch for 150 units. So this is a project that's already complete and done. Again, the project was able to achieve significant cost savings by applying the water demand calculator to the calculations when sizing the water meter and all the water piping. Just going to the next slide. As you can see here, the total savings as a result of using the water demand calculator was actually closer to $500,000. This was the impact fees, the water meters charges, the pipe sizing differences. Instead of having from 1/2-inch to 4-inch, the piping, the pipe sizes range from 1/2-inch to 2-inch. So it really had a big impact on reducing construction costs by tightening up those pipe sizes. And we have a couple of slides that even will show you on a smaller multifamily project as we're going through our example today. So again, one of the things was just the meter size itself showed $88,000, almost $100,000 in savings, and that's not uncommon. As we talked about the last time, the Alliance for Water Efficiency had a report that's worth looking at. It'll show you the ranges of what's out there from right sizing, especially going from what is that, 2 or 3 pipe size differences from 4-inch down to 2-inch, and the water meter connections. It's going to have an impact. And last but not least, the entire Esperanza, the use reduced costs by $43,840 solely for pipe materials and fittings in terms of the savings. So there was a ton of savings opportunities there. There was in-unit water savings estimated to be about 1,106 gallons per dwelling unit. In-unit electricity savings was 2,435 kilowatt hours per dwelling unit per year. And then just cost savings, you can see down here, $278 in electricity cost savings per dwelling unit per year. So just a really great opportunity for construction cost savings and sustainable. Another example of successful use of the water demand calculator, especially in a single family and maybe even townhome style, is Velara. Velara is one of the nation's largest plumbing and HVAC contractors, and they've been pioneering the adoption of the water demand calculator now formally recognized in the California Plumbing Code, but they've been doing it preceding the official adoption. They were getting code exemptions in the areas they were doing it, using it for over 5,000 single-family homes. As they've talked about both in IAPMO's official magazine and on our Authority podcast, which I hosted, they talk about just how much of a competitive advantage it was for them, and they were able to do so, and they just had a lot of success with the utilization of the water demand calculator even prior to its adoption in California. And then last but not least, one that's worth noting is actually one here in my hometown where I live, Phoenix, Arizona. So the Central Station project was 2 towers. One was, I believe, 44 stories. The other one was 22 stories of mixed use. And the water demand calculator was utilized for the residential portions of that building. So those buildings included hospitality, the residential, offices, mercantile spaces, and some kitchen areas as well. So for the residential spaces, the water demand calculator was used to reduce the overall peak GPMs. So in the East Tower, which was the taller of the two, it went from 612 down to 315. And for the West Tower, the total fixture demand flow rate was reduced from 534 GPM down to 474. So not as drastic, but still, and that was in part because there was less residences in the West Tower. But this was one that that was highlighted by the design professional, and actually Michael Rogers with Henderson Engineers. He came on to our Water Demand Calculator Virtual Summit, which is actually just about 2 weeks away now, a little less than. And if you want to attend, we'll have the link here at the end. But he did a session on it, and if you want to see that session, it's available on IAPMO Learn, and that's the QR code right there. That'll take you to the IAPMO Learn section as it pertains to that particular project. So we got a number of resources. You can learn and dive into the details on it as much as you want. And definitely, I think there's some great opportunities for folks to learn more. And the website address is there. All right, so let's go to actually using the water demand calculator. So again, today's seminar is going to largely focus just on how to use it. And we get a lot of questions about that. So first off, if you want to get your own copy of the water demand calculator, here's the QR code. There's the website address. I'll leave that up there for a second. You're going to have to enable macros if you want to use it. And maybe Toju, just in a minute here, if you can just sort of chat on the macros. I think a lot of people have questions about, well, do I need to enable the macros and everything? So I'll give you a moment here in a moment to just kind of help address that question. But just worth noting again from our last seminar that the water demand calculator, it really, the benefits in terms of reducing construction costs, improving sustainability, and then also reducing water age. There's this potential for improvements in public health and safety. These are all some of the positives that come out of it. The Stantec report, which we covered in our last presentation, the ARIP report, which we covered in last presentation, the one I mentioned at the beginning, are great tools for learning more kind of about some of the how-tos. But again, when you download it, it's going to be Excel-based, and you do have to enable macros. Toju, can you cover just a little bit about the macros behind that? Because I think people oftentimes have questions, and if they can get around not using it. But can I just give you a minute here to kind of explain to our participants here the necessity of it?
Okay, so the macros is the main engine behind the water demand calculator. If you have read any of our reports about the water demand calculator and how it works, it actually has 3 different methods of estimating demand in it. So based on your input of number of fixtures and building type, it has to select one of the 3 methods. And then one of the methods, which is the convolution method, actually does the simulation of all the possible combinations of fixture use. And that is what the macro is mainly for. There's no way we can get an output from that method without having the macro run the simulations. And all you need to do is be rest assured that IAPMO is not sending out viruses via its macros. IAPMO is responsible for what it's put in the water demand calculator, but that's about it. We are not putting viruses. So if you can enable the macros, or your organizations will allow you to enable macros, you'll be able to use the water demand calculator. Thank you, Christoph.
Excellent, thanks, Toju. And I think we have an explanation of that on the website too. That's right down there as well. And just to Toju's point, just to piggyback on that, we're sorry that there's bad actors out there. We're not one of them. We're actually using macros for probably what it was originally meant and intended for, which is for positive scientific purposes. So with that, let's go ahead and dive into just the how to use. And I think there's some things that we want to just kind of note here at the start. And this is one, Toju, I think in terms of, I'll probably also ask you to kind of just explain some of how the water demand calculator was developed in this one. Just talking about the data set and reducing it down to efficient fixtures. I think it's worthwhile talking about that with folks. But before Toju explains that, let me just make a note here that, again, Appendix M goes along with the water demand calculator. Appendix M, there's a standalone document. It can also be found in the UPC since 2018 and every version thereafter. And also in the WeStand. Previously it was in Appendix C, but I do believe it looks like it has been moved to Chapter 5 as of the 2023 WeStand. Just worth noting, again, via Appendix M, which is where the focus will be today, Water conserving fixtures, plumbing fixtures, fixture fittings, and appliances shall not exceed the design flow rate in table M102.1. So again, it was high efficiency, and in part that's because the water demand calculator started off in the WE stand prior to the UPC, although it did migrate over there. Toju, can you just touch on for participants again, just on the note of why high efficiency, and I think there's been even some discussions about potentially opening it up into, and I can touch on that too, to higher fixture flow rates, more standard fixtures as opposed to high efficiency fixtures. But if you want to go ahead and start with that, I think that explanation is worthwhile here.
Okay. The water demand calculator was developed using data from over 1,000 residential buildings. And that's how we got the probability of fixture use, which is the duration of, based on the duration of when water is flowing at the different fixtures. And we also were able to monitor the different flow rates from the fixtures in all the buildings. So these flow rates, which are low, which exemplifies efficient fixtures, are what the water demand calculator is suggesting that we should use, because we are looking to the future. We're trying to use less water, and the fixture designs are now designed for efficient use, which use less water, lower flow rates. And so that's what we're aiming for. I know Christoph mentioned something about legal flow rates. Some flow rates are actually higher than what was suggesting, and that's the legal accepted federally. In some states like California, they have lower flow rates. But this was the start for us based on the information we have from the database. And if we can open it to legal fixtures so that everybody can use it based on what is acceptable in their state, we're getting towards that. Christoph.
Excellent, thanks, Toju. And as Toju mentioned, it's currently under discussion as part of the IAPMO Z 1403 technical committee. So we'll see what comes out of there, but it is currently in discussion, as Toju indicated. All right, so as far as how to, the specifics of the water demand calculator and using it, we have several columns here. The first column is the fixture groupings like bathroom fixtures or kitchen fixtures. The next column is the fixtures, specifically individual fixtures, and we're going to touch on these cells in white down here. And just worth noting, any of the cells in white with a white background, those are the editable cells. The cells in light blue are the ones that are not editable. So again, column C here, which is the total number of fixtures, that's what you as the designer will put in there. The probability of use, that is determined by the data behind the water demand calculator. The fixture flow rates, that's the maximums again, and you, based on that table that we showed you before, that you can edit below that, but not above that. And then last but not least is the maximum recommended fixture flow rate. That's basically, it's an exact mirror image or copied image of what's in that table, M102.1, if I remember the number right, that I showed on the previous slide. So that's kind of the main columns. Now, what I want to do is focus just quickly first on these two. So again, you enter your number of fixtures, you enter your flow rate, as I mentioned before. But here at the bottom is what I show. There's this thing for other fixtures. So, the ones up above are pretty self-explanatory, but we get a lot of questions about what is fixture 1, 2, and 3, and it's why is it editable, and what can we do with that? So what other fixtures are allowed? So when you look at these other fixtures, there's this question of what can I use: residential bars, sinks, irrigation systems, pot fillers, or hose bibs? Well, first off, those other fixtures, irrigation systems and hose bibs, are not to be used down there. So if you have any kind of continuous load, even on the hot water side, you don't want to put that down in that section there. It's really what it's meant for is things that mimic other things in the building that's established. So for example, a residential bar sink, it's kind of like a kitchen sink. You can use it for that. A pot filler, kind of like a kitchen sink, because if you wouldn't use the pot filler, you probably would use your kitchen sink. So those are the ones that you could add in there. And then to utilize that, what you would do is you would use the same probability of simultaneous use. That number in there you would put down in that section below. Or if you had a different one that you wanted to use, that would come down to an engineering decision. So you'd have to figure that portion out. So for other fixtures, one of the things that's really specifically common is, the hose bibs and lawn irrigation systems, is that they have a very specific flow rate. Those are dealt with differently, and we'll touch a little bit on that here in just a minute. But just note that the common denominator for both of these is that there's just going to be a straight continuous flow rate of GPM. So if you had kind of a hot water hose bib, sometimes those occur, same sort of thing. All right, one of the other pieces that are worth noting here is up here at the top, the project name and then the click down menu. So again, you can put whatever project name you want, but the drop down menu, when you select that and you go from single family residence to multifamily, what you'll see is this other pop up over here, this other, unhidden series of calculations. And these are important. And Toju, I'm going to have you touch on a little bit the simultaneous demand and what you guys noticed from single family to multifamily, and maybe give an explanation here. But what you're going to have here is a total number of apartments in the building, and so however many you have. In our case, it's going to be, for example, it'd be 21. And then for whatever segment of pipe you're dealing with, however many apartments are downstream of that, however many in that portion of the calculation is what you'll put down in that lower number. You'll see it in our example as we run through it. Toju, do you want to just kind of explain to the folks here in terms of what was discovered with the single family versus a multifamily application, just to kind of give them the reasoning of why that particular one was added?
Yes. So we did not have data for the multifamily buildings, but in an apartment buildings, there are multiple single family buildings. So we used the single family data we had and put them together to assume there were a multifamily building. And what we see is that the fixture count increases, but the probability of use, the peak hour probability of use decreases. And that's because not all the fixtures in the building, or not all the units in the building are in peak hour use simultaneously. And so we see there's a decrease in probability of use in a multifamily building as the number of units in the building increase. And that's what we reflected there. If we were to use the single family p-values to calculate, to estimate peak demand for multifamily buildings, we will be overestimating, and we've seen it in our results. So we added that fact into the calculator. So for multifamily building, depending on the number of units in the building or the section you're calculating for, the probability of use changes. Christoph?
Excellent. Thank you, Toju. All right, so let's go to our example of 21 apartment units. So let's focus again on that, what Toju was just kind of describing a little bit here, the total number of apartments in the building and total number of apartments in this calculation. So we're going to start off looking at the water main coming into this apartment complex. So again, we're going to put 21 apartments in the total for the building. And then again, because that portion of the piping is dealing with all 21 apartments, we're going to go ahead and put in our 21 apartments in the calculation. Then we're going to fill that down here, the 21 combination bathtub showers, 21 faucet lavatories, so on and so forth for each one of those units. So again, these numbers coincide with that 21 total numbers. And again, each of these apartment units is a 1-bathroom apartment unit. After we fill in all of that information, we're going to press that green button, Run Water Demand Calculator. And we're going to get a result here on the right-hand side of a total number of fixtures in the calculation of 126 and a 99th percentile demand flow rate of 18.6 GPM. So if you were to run this exact same calculation through the Hunter's curve, that peak flow rate was going to be 80 GPM. So we see a difference of, instead of having a main of 80 GPM, we only need a main to size based off of 18.6 GPM. And if from the last class, if you recall, that 18.6 is likely still on the factor of 2 times the higher than the GPM that will actually be observed as a 99th percentile peak flow rate. So, likely it's probably going to be around 9 to 10 GPM is going to be the actual peak flow rate that's observed in this building if a sensor was put on. Now, remember what can and can't be added to the water demand calculator. So again, we didn't put in hose bibs, we didn't put in any irrigation systems. So again, those are continuous loads. So irrigation systems, let's say you had a 2.5 GPM or 20 GPM, depending on what type of irrigation you have, peak flow rate on your irrigation system, you would likely just add that on to the 18.6 that was there before. That said, some engineers do look at, well, what's the time that the irrigation system is going on? And so there are discussions and arguments that happen that says, well, the irrigation system is not going to happen at the peak load, which is likely in the morning hours when people, the highest peak load is likely to occur. So some engineers do look at putting that as a separate load and don't use that. And there's certainly discussions in Z1403 and others areas that are ongoing around this. So expect to see a little bit more definition around this in the near future. Hose bibs, however, that's very specifically covered in the water demand calculator. And that is just an additive load. So the key note here is that, oops, sorry, go back, is that in the Appendix M, you look at the number of hose bibs and the GPM, and you account for one of those hose bibs, however many there are, to be on. So if you had one hose bib, you assume 5 GPM for that one, you add that. If you had 6 hose bibs, then you still would only assume one of the 6 is on, and you would add that 5 GPM to the 18.6 to end up with a 23.6 GPM. And that's exactly straight from M102.5, where it says where there is more than one hose bib installed on the plumbing system, the demand for only one hose bib shall be added. So again, this is just the continuous supply demand irrigation is similar, but you know, there are arguments and people that do make different you know, design decisions, engineering decisions around that. So right now, irrigation and hose bibs you have to add based on M102.5, but there are potentially opportunities to work with your HJ or make more engineering decisions about right sizing. All right, so let's take all the information we have now and kind of put it to work. And we're going to be flipping through a lot of slides here pretty quick. Now, we're going to look at Appendix A from the UPC, and we're not going to spend too much time on this because hopefully it's pretty familiar to most of you here on the call today, but let's just run through it. So let's say we had an available pressure at our water meter of 70 PSI. Let's say we had a pressure loss due to elevation. So we had 60-foot tall building times 0.43 PSI per foot equals about a 25.8 PSI loss. So you take your 70 minus your 25.8 and you end up with, 44.2 PSI available pressure. Then you need 20 PSI for a pressure balancing shower valve on the 6th floor. So you got to subtract that off your available pressure. So now you only have 24.2 PSI left. And you have friction losses due to fittings and valves. So let's say you had 180 feet times a fitting factor of 1.5 equates to 270 feet. That's your equivalent feet. The next step is you take that available pressure of 24.2 PSI divided by 270 feet equals 0.0896 PSI per foot. Remember, we size typically based off of a PSI available per 100 lineal feet. So you take 100 feet times your 0.0896 PSI, and you're left with basically a 9.0 PSI per 100 lineal foot. So hopefully those calculations are all pretty review for everybody here on the call. So if you go to your charts in the back and you look at the bottom there, that's your friction loss in head, pounds per square inch per 100 foot of length. So your 9 PSI per 100 lineal feet is right located there between the 8 and the 10. There's a line. So for that, before we get to that though, and then on the y-axis, you have your GPM. So again, for the water demand calculator, our peak flow rate was 18.96 GPM. Keep in mind that the values on the y-axis are logarithmic, similar to the x-axis. So your scale, you have to look always in between the values. You can't just go based on the overall. And so they're always going to get kind of pushed up a little bit. So it always kind of go just slightly higher because of that. So if we were to draw our line for 9 PSI per 100 lineal feet, here's the line. Now, one thing to note, velocities, which are these negative slope lines, they cut across multiple PSI per 100 lineal feet. So it is important based on the pipe material. In this case, we're going to assume copper to not go above the, don't go into this area of your velocity. So again, you can see here, 9 PSI per 100 lineal feet, you can get pretty high up there. It cuts all the way up to like a 6-inch line. But even with a, even with that higher, even with that PSI per 100 lineal feet kind of going vertically there, you want to make sure you stay kind of in this lower region. So below, you want to always be below the velocity line, and then you always want to be to the left of the PSI per 100 lineal foot line in terms of whatever your pipe size selection is. So in our case, our 18.6 GPM, if we were to draw another line here, it intersects right there, slightly over a 1. So we want to make sure that we end up going up to the next size of 1.25 inches. Then 18 GPM is where we change to a 1 inch. 9 GPM is where we change to a 3/4 inch. And then 3.25 GPM is where we change on a 1/2 inch. And again, these are all below that 8 foot per second for cold water. So If you do a quick comparison, and you were to size the system first with the Hunter's curve, based on that 80 GPM, you would have pipe sizes all the way from 1/2 inch to 2.5 inch with the Hunter's curve method. With the water demand calculator, as we just showed out, your pipe size ranges are from 1/2 inch to 1.25 inches. Just worth noting again on the velocity side with hot water, one thing is that right now for copper, as an example, the Copper Development Association indicates 4 to 5 feet per second on the hot water side, although there has been some research done that's indicating in other countries where they cap the limit for copper at 1 to 2 feet per second. So just be mindful. There might be a lot more conversations happening in that topic around the industry. And so just be aware that there might be some upcoming guidance changes here in the near future. So we'll see what happens. So again, you'll notice 1/2 inch to 2.5 inch versus 1/2 inch to 1.25 inches. It's all still the same number of lengths, but you have a situation now where your pipe sizes are smaller. They're right sized. So let's look at one of our units. And so this is kind of the template unit that we have. You have a cold water line coming in that goes from clothes washer to kitchen sink. Your dishwasher is the hot water's tap off for the dishwashers only. Your combination tub and shower, water closet, and lab. So we're going to just take a look at the cold water. The lessons are basically the same for the hot water. And if we look at the water demand calculator, the last time we left it, we had our water size coming in. Now, if you want to save your calculation, you press this sort of light yellow tan colored button on the lower left-hand corner. That's download result. This button will come up and it's going to drop a version of the calculations into your download folder. It looks like this. These are the ones that you can import to make PDFs of to put in a binder. You can take these from Excel and link them into Revit. There's a ton of different options and ways to utilize this in your design. So let's go back to the water demand calculator. There's a couple different ways that people like to go ahead and utilize it. For this one, we're going to press the red button, the reset button, because we're going to be doing one of the units. But one of the other ways you can do it is kind of continually add the numbers, and you kind of just make sure you update the sections up here in your fixture units. No right or wrong way, but there is an opportunity to reset the water demand calculator all to 0 as you're using it. So for what it's worth. All right, so time to start sizing the piping. So if we look at our unit here, the first thing we want to do is assign GPMs and then size each fixture branch. So we're going to do that. That's going to be based off the code. Again, Appendix A covers all of that. But the GPMs here we can drop in for each one of these. So again, remember that the fixture flow rates, we fill those in that I think we had A, B, C, D, E, so that column E there. So we'll go ahead and add that. And then what we're going to look at is the branch sizes. Keep in mind we're probably going to be looking at a few branch sizes here, probably 3/4 or 1/2 inch, more likely than not. So let's do the next steps in our calculator for this one unit. So first off, you're going to enter the total number of apartments in the building. So that's still important. That's still 21. Even though we're only doing one apartment in this building, we still have to have the 21 apartments. Then you're going to have the total number of apartments in this calculation. So in this case, we're going to have the 1 there for that. The next step is going to be putting in the fixture unit. So again, in this case, we're doing the cold water. So it's going to be combination bath shower, faucet, water closet, the kitchen sink, and then the clothes washer. For the hot water line, the one difference would have been the clothes washer would be eliminated, and then you would have had the dishwasher because the hot water tap was off the dishwasher for that section of pipe. And then you're going to press that green button of Run Water Demand Calculator. And again, what we end up with is for 5 fixtures, we have a peak flow rate of 9 GPM per the water demand calculator. So for that section of piping that's coming in there, the cold water, 9 GPM equates to a 3/4 inch. And then we move on to the next section of piping there, just downstream of that for the kitchen sink, tub shower, water closet, and lavatory. So going back to the water demand calculator, same thing. All the values up here at the top stay the same because we're still within that 1 unit. And then we go combination bath shower, lavatory faucet, water closet, and then the kitchen sink. Press that green button of the Run Water Demand Calculator. This segment of piping equates to 7.7 GPM. So that equates to still a 3/4 inch. Then we go downstream again for that next segment of pipe for the tub shower, water closet, and lavatory. Again, we're going to put the inputs in on our in our column here. Again, it's still 1 unit. Press the Run Water Demand Calculator button. For 3 fixtures, we have a flow rate of 7.0 GPM. So 7.0 GPM equates to a 3/4 inch. So that part stays 3/4 inch. Next, we'll go downstream again to just a combination tub shower and, or excuse me, for the water closet and lav. We'll fill that in. Run Water Demand Calculator, 3 GPM. 3 GPM is less than that 3.25 GPM, so we have a 1/2 inch. Now, the last fixture is served off the fixture branch, so we have that covered via Appendix A. Let's start doing multiple units within the system. So in this case, we're going to look at that riser that connects to the 2 apartment bathrooms. This is the first apartment that we just did. Here's the other one. That's a mirror image of it. So we have 3/4 inch tap offs off of that. Our big change, we got to change from 1 unit to 2 units over here. And then we have 2 units for each one of the other, we have 2 of every single fixture type for the cold water side. Press that green button of the Run Water Demand Calculator, and our peak flow rate ends up being 10.5 GPM. So 10.5 GPM, that is less than 1 inch, so that becomes a 1 inch pipe. Moving on, now we got 4 units. Same thing, press that green button, 11.2 GPM. 11.2 GPM still is less than that 1 inch. We continue down. Let's go down. Now we're doing 6 apartment units. For 6 apartment units, we change the number up here on the top right. We're still at 21 total, but 6 is what we're calculating in this segment of pipe. We're going to change the numbers here to 6 units total for 6 of each fixture type. We press the green button for the Run Water Demand Calculator, and when we do, we end up with a total of 30 units or 30 fixtures spread across the 6 units, and we end up with a peak flow rate of 13.2 GPM, which is still under the 1 inch. Let's go down again. Same thing. Now we have 8 units, so we have 8 of every fixture. We press that green button, Run Water Demand Calculator. What we end up with is a total of 40 fixtures at 14.5 GPM, which equates to still a 1 inch. So we have a 1 inch riser going all the way up, serving 8 apartment units so far. Now we're up to 10. So again, we changed the number in the total apartments in this calculation. We still have 21 total apartments in the building. We have 10 of each fixture type. Press the green button, Run Water Demand Calculator. Now we have 50 total fixtures at 15.1 GPM. So that's still a 1 inch line. Now we add 1 more unit. Again, we have a mechanical room on the floor of this side of the tower. So we add 1 more unit. So we're at 11 in the total number of apartments in this calculation, 11 of each fixture type. Run the green Water Demand Calculator button. For 55 fixtures, we end up with a peak flow rate of 16 GPM, which that equates still to a 1 inch. These buildings are twins. So again, we said 21 in total, very, very close, other than having that extra one on the ground floor on our, I guess, our left tower. But going to the right tower, everything else stays the same up until the 10 units. So we have a 1 inch line there. So now we have 2 1 inch lines coming together from this side. The question is, now we have this segment of pipe here. And we know what our flow rate on the incoming water service main, that was our 18.6 GPM that we had before. Again, that was all 21 apartment types. So again, we have that segment that's been indicated. So that's where our 18.6 GPM flow rate equates to that 1 1/4 inch water service entrance. Now, the one question is this line here. So this is just upstream of our water heater. And so it does include all 21 units of hot and 11 units of cold. So how do we do this? We still just use the 21 total number of apartments in the building. So it's 21. But the one difference is for this section is we add the dishwashers right here to all those units, because we have to account for those dishwashers in that section, just like we did on the incoming water service main. We should have had that. So we press that Run Water Demand Calculator button, and the result is 18.5 GPM for that segment of pipe. So as you notice, it's not like a linear kind of reduction. It does kind of only go down by 0.1. And so sometimes people have questions about this. And Toju, again, I think the simultaneous use, maybe you can touch on some of the the differences here in a moment for our audience, because sometimes that question does come up, like the differences, and how much it changes from a certain number of apartments and bathrooms to others, seems kind of a little bit at random. I would think we get questions about that. It's not at random. It's actually very intentional, but it does go through different phases. But that's one of the things that you do want to look at is, thinking about, again, that segment of pipe, what is downstream of it? And if it is upstream of like the makeup water, the cold water makeup to a water heater, you do want to include hot water fixtures on that line. If it doesn't include hot water fixtures, then you can go ahead and remove it, like you can do over here on this section, and then this section over here. There's no hot water lines over there. Toju, can you just talk a little bit about that, some of the not linear, results you get due to simultaneous use? I think we had a white paper on this as well that's worth touching here on for our participants.
Yes, but a lot of things is going on when you're increasing the fixture counts, or depending on the section you're adding, or if you're doing just hot or cold water. For example, you might be adding a unit with a bathtub and shower compared to another unit with just shower. The flow rates are different. So and when you're increasing the number of units in the building, remember I talked about the probability of use dropping. And so the change in the demand flow rate is not necessarily linear or assigned to one particular fixture, because we're looking at the combination of all the fixtures and then the 99th percentile. So there's a whole lot of statistics and calculations that went into this, and because of the p-values and the corresponding flow rates, these are the 99th percentile that we are getting with very high confidence.
Excellent, thanks, Toju. All right, so let's take a quick look at hot water only. So, if we count for the hot water, the hot water only sections, and again, we eliminate basically the water closet from our calculation for the individual units based on fixture units. We end up, based on the fixture unit method, of a 69 GPM hot water line that's going into, from the water heater, or scores a cold water makeup into the water heater, and then the hot water main coming out of it. So instead of what we ended up having, which was the 18.5 GPM, which equated to 1.25 inches, we would have ended up with a 2-inch hot water main. So we had a difference of 1.25 inches versus 2-inch for the hot water side. So again, that line has all 21 units of hot. So based off of that, if we do the hot water only, again, we eliminated the toilets. The calculator, what we show is, 18.3 GPM for 105 fixtures. So it's a difference between, what did I say, going back, 69 GPM versus 1.25 inches at 18.3 GPM. So, it's definitely one of those that you're going to get some differences there. And we're going to show you just in a little bit some of the potential energy savings from that. So we'll touch on that here in just a minute. Before we do, just want to make note that we did release a subscription-based water demand calculator specifically for multi-units like this. And so, just want to kind of just take a brief mention, because we got a lot of questions of ways like, how can you make the water demand calculator faster? Well, one thing we noticed is that people that got very familiar with the water demand calculator already saw their design times going down overall. Especially when you consider that the Hunter's curve method, you have to go from counting the number of fixtures, converting to water supply fixture units, and then converting to GPM. With the water demand calculator, you count your number of fixtures and you go straight to GPM. So it eliminates that entire translation step. So a lot of the design professionals we talk to that regularly use the water demand calculator, they saw a reduction in 50%. But we still have people that were like, it'd be great if I didn't have to keep inputting those numbers and I could make that part go faster. So one of the things that we looked at, similar to how we provide an illustrated training manual or a guide to important code changes for the UPC and the UMC, where the UPC and UMC are free documents. We have these documents that you can pay for that give you some added value in terms of identifying code changes or providing additional training material around how to utilize the codes. We decided we were going to do the same thing with the water demand calculator. So that free water demand calculator link page that I showed you before, that's for a free version. The macros with Excel, that's always going to be a free version out there. But we did create a subscription base kind of following the ITM guide to important code change model. It's $29 a month, and then there's a yearly price, I think, of $290 if I remember right. And in essence, it's a web-based as opposed to Excel-based app. So you just go log onto a website, it can save your projects, and it looks like this. You put in you can create a project or use an existing project, and then you can create reports off of this. But in essence, there's 4 screens that you use to kind of do the same stuff we just did now. So the first screen is basically creating templates, and that's really the engine behind this thing. Is you can create templates for your apartment. So in this case, we had that one template of a that single bathroom apartment for all 21. So if you input those numbers here, you can do that. And then if you click that green button down here, it'll take you to the next page. This is where you start identifying points of interest. So you can select however many points of interest you want. So however many pipe segments you want to calculate the peak flow rate for. So, you can do hot water, cold water, there's drop-down menus here for certain calculations that you run. If you only want to have a test run in there and you don't want to include that in a final report, you can uncheck that here. If you're in multiple pressure zones, you can identify that. You can do as many points of interest as you want. You press the green button down there that says next. It'll take you to this third slide. This one just got to be mindful of. As I mentioned before, you can have the points of interest. You can name them whatever you want. So you can name them based on a pipe segment chart, or if you have a specific like tower or something like that. So you click on that down, there's a select drop down menu here. And then for each segment point, you can go through, you can give it the parameters. So you can tell it how many apartments are in that calculation. And then if you have any outdoor fixtures, like the hose bibs or irrigations that we talked about, you can add that here in terms of the number. There's gonna be some nice little warning segments that'll pop up. So for example, in this case, this one was for cold water only. So if you had one for hot water only, you can definitely do that. It'll help identify that to help kind of nudge you to remember where you are at in your system. And then if you go to again, this is just a similar slide. This is one of the other points here. Again, this is cold water only, kind of points you to that. Then your next one, which is your fourth one, for each point of interest, you're going to identify what your flow rates are for that. Now, the good news is those should come over from one to one, from one to the other, but you do have some editability there if you so desire. And then you press that green button that says calculate. And you're going to get a report. Now, this one is a little bit simpler because, again, that drop-down menu is just going to show you what the calculations are. In this test trial, it ends up with the same exact calculations as the WDC, the water demand calculator, that free version we had. You can download them in terms of Excel, I believe, and PDF. So it gives you different options in terms of how to get those reports, and you can put those on your plans, submit them in a binder, submit them electronically, however you want. But again, all the values are down here, this gray box down below, and it gives you a nice summary of what you put in before. All right, so let's look real quick, kind of going back, whichever way you want to use, the free version or the WDC Pro version. One thing worth noting is that for each of your different pipe segment lengths, again, comparing the Appendix A Hunter's curve method versus the water demand calculator method, you'll notice that there's some differences in terms of sizes. So again, we went from a 2.5-inch water main down to 1.25 inches. That next pipe segment went from 2 inch to 1.25 inches, 2 inch to 1 inch. We had some areas that were similar. Again, especially as we get further into the units, they end up being very similar. But again, we had other pipe segments, 1.5 inches down to 1 inch, 3/4, 3/4, and then other ones where you had 1.5 inches all the way 1.25 inches, that all went down to 1 inch. So that was our risers coming up here. Now, looking at dollars per lineal foot, again, by eliminating these largest pipe sizes, we got, especially on our mains, we have a comparison of material cost savings of $27.92 per lineal foot versus $9.79 per lineal foot. So that's a lot of our starting functions. And again, that's based off of data from Ferguson back in late 2024. But that gives you an idea of what some of those cost savings opportunities are on the engineering side. All right, so let's real quick, putting it together, the water and energy savings opportunities. Again, we're probably looking, somewhere in the range of 500 gallons per dwelling unit, as high as 1,000 gallons or more per dwelling unit per year. But let's look at specifically energy savings. So if we look at our case here for a hot water main, specifically going from a 2-inch down to 1.25 inches, based on the ASPE Legionella Design Guide, there's a difference in BTU per 100 lineal feet. Again, we'll just take assumption of 140 Fahrenheit water. Let's say they're using point of use mixing valves in different locations. They're worried about waterborne pathogens because of that building type falling under ASHRAE 188 and other documents such as ASPE Legionella Design Guide and the NASEM report. So they want to see elevated temperatures in there. So click the button too fast. On the hot water pipe sizing results, again, we get the 1.25 inch and we go from a 2 inch. So now the savings maybe are not quite as great because we only go from $19.51 per lineal foot down to a starting point of $9.79 per lineal foot, but it's still up there. It still helps out even in that sense. So just to wrap things up here, just a couple of resources. I mentioned a few times at the beginning here, we have our Water Demand Calculator Summit coming up on November 5th from 9 a.m. to 1 p.m. Pacific. The QR code and registration is there. If you look at your ASPE pipeline, we did offer ASPE members a coupon code. I believe IAPMO members have a coupon code as well. So if you want to look at that and attend, we'd love to have you. The theme this year is breakthrough. And we definitely have made some pretty significant breakthroughs this year in terms of the water demand calculator. So very excited to share those with the industry. I touched on the WDC Pro. Again, that's the website. If you go to wdcpro.iapmo.org, that's where you can sign up. If you have questions, by all means, on either of those, feel free to reach out to myself or Toju or any of our colleagues. There is our contact information. And the only other key takeaway I have is for all of you is just stay tuned for our non-residential to commercial building sizes. Toju, Dan, Randy, IAPMO, we're all working really hard at getting data. We still need a lot more. We would love to collaborate with you on getting that data if you have opportunity. So please reach out. But we also are making some great strides as well. So would love to chat. So that concludes the formal portion of the presentation. I think we now have time for questions if anybody has them.
Oh boy, there was a lot of questions, Christoph, and there were a lot of good ones. And I would also say to everybody listening out there, a lot of the questions that you were asking were actually covered in the last webinar that we did with the fine folks from IAPMO. So definitely check that out on our YouTube channel. But I did have a number of pretty good ones, and I'm glad we got time to talk about this. So there was actually quite a few people in there asking about the difference, or if it would make a difference in the water demand calculator with the use of 1.28 versus 1.6 gallon per flush toilets. Is the fill rate still the same? Is that going to change anything? Is there anything that you would want to add to that, I guess?
I'll probably ask Toju to jump in on this one, but from my understanding, I don't think a 1.6 gallon per flush toilet and a 1.28 gallon per flush toilet have a different flow rate. I think they're pretty similar. Toju, can you chime in on that? Do you recall what the data said in terms of flow rates and whatnot?
I don't think we did a specific analysis on the difference, but if they have the same flow rate, the probability of use might be slightly higher for the 1.6, given it's taking a longer time to flow, to fill the tank. But what we have in the calculator right now is 1.28.
Perfect. Yeah, and one of the questions that was asked by a self-proclaimed old timer who used to see toilets, at fill rates of, multiple gallons per minute, 5, 6, 7 gallons per minute just to fill up that giant tank that they used to use, right? So, but that's a great one. The next question that I thought was a really good one, if you have a multifamily type building where each unit has different fixture types and flow rates in it, do you have any suggestions on how to deal with that versus just kind of the cookie cutter same, in every single unit?
Yeah, and that's actually, I think, one of those topics that's coming out of Z1403 as well, if I recall one of the latest conversations. One of the things is to look at adding more fixture types because of that exact occurrence, if I remember the conversation. So be on the lookout. There might be a revised version of the water demand calculator, but the committee has to look at that. But that was a topic of conversation. The other one is just to utilize the higher flow rate for now. Toju, anything you want to add to that one? I'm trying to think here if there's any other things in terms of if you had fixture unit types in a single unit of apartment.
Sorry, what was the question? I was answering questions online.
No, and I saw you answering the questions, Toju, and I appreciate it because there's some good ones in there. The question was, if you've got these multifamily buildings, right, and each unit, in your examples have the same fixtures in each unit or very similar fixtures. Mm-hmm. What happens if you have units that are very different from one another with different fixtures and different flow requirements, and how would that affect things, I guess?
You will still go with the same way. The only thing is you might run into a problem when you add say a studio, and you've been adding 2 units or 1 unit, and then you add a studio, and by the time you increase the number of units, the probability drops such that the demand will drop. So that's where I would say you use caution. But if the building is all of it 2 units or 1 unit, and then there's 1 studio, don't add the studio as a unit, because it's not growing in the same way that the other units are growing. So it doesn't affect the output, and then you start feeling there's something wrong with the calculator.
Cool. A couple more questions here that I'll throw you some softballs here. There's a couple of tough ones that I don't want to throw at you today. I don't think we got the time. And I know we talked about this the last time, but can you guys talk about where the water demand calculator is currently accepted? Because obviously it's not accepted everywhere just yet, but there was quite a few questions in there on where is it accepted.
Certainly. So right now, if you go onto that water demand calculator website that Max so kindly put in there, there's a fact sheet that shows on page 3 of the fact sheet that shows where it's currently adopted that we're aware of. But it's 12 states, and it's everything from UPC adopting states to IPC adopting states and jurisdictions to, basically state, developed codes like Wisconsin as well. So, but that's everywhere from California to New Jersey at this time, along with 6 other cities that have adopted it. Charlotte Water Department has adopted it. City of Phoenix, where I live, just recently adopted it. And one of the more recent adoptions is Castle Rock, Colorado, becoming the first city in Colorado to adopt it, in part because they want that water conservation and right sizing and better leak detection that we mentioned in our last presentation. So that map is there, and we did cover that, I think, in the presentation. But even if in areas where it hasn't been adopted, as I mentioned and showed in the presentation, Velara was using the water demand calculator prior to the official adoption of the water demand calculator. Same in Phoenix. That Central Station project was done before the water demand calculator was even being looked at. There's a lot of places around the country where design professionals, plumbing engineers are using the water demand calculator to provide added value to their clients. So when you look at the adoption, yeah, that helps because you don't have to go for a code modification or for a alternate and approved method. But there's certainly still opportunities to use it even if your jurisdiction hasn't officially adopted it.
Perfect. Yeah. And another line, and again, this is one of the ones that we covered with the last webinar, but currently right now, you guys are doing single family and multifamily. There was a lot of questions about different building types. Those you guys have a timeline for, and you guys talked about that before. One of the ones that I thought was interesting though, and I think we talked about it the last time, was what about mixed use buildings where you've got residential, multifamily, and then on the ground floor, you've got commercial type applications? How would that, is that something that you guys can accommodate?
Yep, the Central Station project, as I mentioned before, that it utilized exactly that, and definitely would encourage our participants here today to check out that link I showed at the beginning, which was for the IAPMO Learn. It was a recorded version of the Water Demand Calculator Summit back from last year. In essence, what the most common way that people size right now with the Water Demand Calculator, those types of occupancies is mixed use, is to use the Hunter's curve for the non-residential sections, and then we use the water demand calculator for the residential sections, and then to combine by addition those 2 numbers. There's nowhere in the water demand calculator right now to add the non-residential the non-residential fixtures. Again, that's another topic as part of Z1403 that they're looking to address. But the residential, the basic topic is for that combined water main that's coming in prior to it separating for the mercantile and residential spaces. Calculate the water demand calculator for how many apartment units or condos are downstream of that segment of pipe. You also count up your total number of fixtures via the Hunter's curve and convert that to the GPM downstream of that segment of pipe, and then you take the water demand calculator number and you add it to the Hunter's curve number, and that's where you end up with your final GPM that you can use to size your pipe via Appendix A.
Perfect. I guess one more softball I'll throw at you before we end the day. Will IAPMO help with adoption and or approval with other jurisdictions moving forward? What are you guys doing to help out with that? Or do you just call them all personally, Christoph?
No, IAPMO, we do help with adoptions. As far as approvals, that comes to the HJ. But if there is a jurisdiction that you're looking at getting adoption in, we are happy to be part of the process. We provide support. That's actually a large part of my role. But Toju, Dan, Randy, we've all gotten involved in some way, shape, or form with adoptions. It is a little bit different, from one HJ to the next, because every state and city does a little bit differently. But we do get involved, and we're happy to provide explanations and provide training. We provide a lot of resources that are recorded and written down. So there's a plethora of information out there, and we also personally get involved in terms of providing information or training, education, or even testimony as needed. So by all means, please reach out if you are in a place that's not included in that map, and we'd be happy to collaborate together to make it possible for you to use it more easily in the cities and towns that you all live and work in.
Perfect. So we're going to finish things out here. I do just want to say that for anybody that had a question, that typed it all in, took the time to type it in, we do want to make sure we try to get back to you, and we'll work with Christoph and Toju to make sure that happened. And Toju, thank you so much for answering so many of those questions in the question pane. I do appreciate that too. Before we finish up, I do just want to say within the chat window, Max actually linked over to our YouTube channel with the previous webinar that we did with the folks from IAPMO here. And so from there, definitely check that out. A lot of good information in there. And if you guys have any questions on anything plumbing or hydronics related, definitely give us a call at our tech support team in Milwaukee is definitely happy to help. And Christoph, Toju, thank you so much for your time today. We really appreciate it. And I hope everybody else that was listening appreciated it as much as I did. And we'll see you next month with Max Rohr on pressure reducing valves. Thanks, guys.
Thanks all.
Thank you.